Hi, Assalamualaikum and hello everyone. I'm Muhammad ISKANDAR. I'm gonna present about instrumentation and measurement in biomedical group assignment, which is computer system and nervous system. So here we have a group members. We have me, Iskandar, AININ SOFEA, SAMAA TAREQ, AQILAH, and lastly SYAQILLA. So for the part 1, engineering system versus human body system. So for the first part, introduction, I'm going to talk about computer system. What is computer system? It is composed of electronic components and programming, operates in a manner that's surprisingly similar to how the human nervous system functions. And how about nervous system? It acts as the body's command center, collecting sensory information, processing it in the brain and spinal cord, and then triggering the appropriate responses.
A computer system works by processing data through a series of connected components. First, the user input data using devices like mouse, keyboard, or microphone. This data is sent to the control unit, which directs the flow of operation inside the CPU. The arithmetic logic unit, or ALU, then processes the data by performing mathematical and logical operations. During this stage, temporary data is stored in the primary memory, or RAM. If needed, data is also saved permanently in the secondary memory, like a hard disk or SSD. Finally, the processed result is displayed through output devices such as monitors or printers. This entire flow, from input to processing to output, is how a computer system operates to complete tasks.
Let's begin with the working principle of the nervous system. The process starts when environmental stimuli like temperature or pressure are detected by sensory receptors. These signals travel through afferent sensory neurons to the central nervous system made up of the brain and spinal cord. Here, the information is processed and interpreted. Then the CNS send commands to the efferent motor neurons to effectors like muscles or glands, resulting in either voluntary or involuntary responses. This system functions much like an input, process, output model.
This table shows a comparison between the computer system and the human nervous system. Both systems follows a similar structure. Input devices in a computer, like a keyboard or microphone, are similar to our sensory organs such as the eyes and the skin, which detects stimuli. The CPU acts as the computer's processing unit, just like the brain, and the spinal cord process information in the nervous system. Output devices such as monitor and printer parallel our muscles and glands, which carry out responses. Data in computers is stored in RAM or SSDs, while in the nervous system, memory is stored in short and long term in the brain. The control unit in computer directs operation, just like specific brain regions control body functions. Finally, both systems rely on signal transfer. Computer use electrical signals in wires, whereas the nervous system use nerve impulses transmitted through neurons. This comparison highlights how biological systems and man-made systems are closely aligned in function and structure.
Next, let's look at how the computer system differs from the nervous system. Firstly, the type of signal is different. Computers use binary electrical signals, while the nervous system relies on electrochemical impulses. In terms of powers, computers run on electricity while the brain uses glucose and ATP. Other than that, computers must be manually programmed, whereas our nervous system learns from experience through neuroplasticity. Finally, the brain can adapt and reroute when damaged, while computers may crash completely when there's a system failure.
So I'm going to continue for the part 2, medical equipment based on the system. So the relevant medical device that we're going to talking about is cochlear implant. The relationship between engineering system and physiological systems provides crucial insight into the design and development of a biomedical device. In this context, the computer system can be conceptually and functionally compared to the human nervous system. Both systems rely on data processing, information transmission, and output control mechanism. A computer system processes input data using a central processing unit we call as CPU, transmits information via buses and circuits, and delivers output through peripherals. relevant biomedical device that bridges this analogy is the cochlear implant. A cochlear implant is an advanced neuroprosthetic device designed to restore hearing to individuals with severe to profound sensorineural hearing loss. It mimics the information processing function of both the computer system and the nervous system, acting as a substitute for damaged part of the ear. For the functional comparison, it divided into 4 aspects. For the first one is input or reception. Computer system accepts input via sensor or input devices. Nervous system receives stimuli from sensory organs like ears, eyes and skin. And cochlear implant use a microphone to receive external sound signals, or we call as analog input. So for the next one is processing. Computer system, the CPU processes data through algorithm and software. And for the nervous system, the brain processes neural signals to produce meaning and response. And for the last is cochlear implant. A speech processor converts sound into digital signals and filters them based on the relevant frequencies. And the third one is transmission. For the computer system part, it uses electrical signals through circuits and buses. For the nervous system part, it transmits impulses via neurons and synapses. And for the cochlear implant part, it processes digital signals via a transmitter coil to an implant receiver inside the skull. And last but not least is output, or we call as action. For the computer system part, it sends output to the device like speaker and screen. For the nervous system part, it activates muscle or glands as a physiological responses. And for the cochlear implant part, it sends electrical impulses to the auditory nerve, which the brain interprets as sounds.
Okay, so now I'm gonna explain about the function and components for the cochlear implants. So for the function, the cochlear implant is a medical device that restores hearing for people with severe to profound sensory neural hearing loss. So unlike hearing aids, which only amplifies the sound, cochlear implants directly stimulate the auditory nerve using electrical signals. As for the components, we have 7. The first one is microphone, the second one is speech processor, the third one is transmitter, the fourth one is receiver or stimulator, the fifth one is electrode array, the sixth one is cochlea, and the seventh one is auditory nerve.
Let me briefly explain the block diagram of the cochlear implant system. It has 2 main units, the external unit and the internal unit. The external part, also called the speech processor, contains a digital signal processor, DSP, a power amplifier, and an RF transmitter. The DSP captures sounds, extracts important features, and converts them into a digital bit stream. It also stores patient-related data called maps. This processed data is wirelessly sent to the internal unit through an RF link. The internal part includes an RF receiver and a stimulator. It doesn't use its own battery. Instead, it gets power from the RF signal. The stimulator decodes the bit stream and converts it into electrical impulses, which are delivered to specific electrodes in the cochlea to stimulate the auditory nerves. This whole system works together to recreate hearing by mimicking how the nervous system processes sound.
Moving on to the real-world applications, the cochlear implant is a strong example of engineering mimicking biology. The microphone acts like an input device, the speech processor works like a CPU, and electrode array sends output signals directly to the auditory nerve. Clinically, this device helps children born with hearing loss develop speech and language. For adults, especially those affected by age-related hearing loss, it restores the ability to hear and communicate. Furthermore, bilateral and hybrid implants allow even better sound clarity and preserve natural hearing. Other than that, cochlear implants have significantly improved medical treatments and diagnostics. Instead of just amplifying sound, they restore auditory function at the neural level. This reduces the need for special education and support services. In diagnostic, tools like audiometry, ABR, and imaging help identify suitable patients before surgery. Post-surgery, neuroresponse telemetry, and impedance telemetry are used to check implant function and customize sound mapping for each individual patient.
So now I'm gonna be talking about the engineering innovation for the cochlear implants. So the first big innovation is the miniaturization of components, which make components smaller and easier to manage. The second one is digital signal processing, or DSP. The third one is wireless technology and telemetry. And the fourth one is MRI compatible implants, so patients with the implants don't need to be afraid when they're doing MRI. And then the last one is mobile device integration.
Now, let's explore how engineering innovations improve biomedical devices. Miniaturization makes implants like pacemaker and cochlear implants smaller and more comfortable. In addition, digital signal processing helps filter noise and improve sound clarity. For wireless telemetry, it allows real-time monitoring and device adjustment without surgery. And for MI-compatible materials, it makes it safer for patients to undergo imaging. And lastly, with Bluetooth integration, users can control settings from their smartphone, giving them more autonomy and confidence.
Hi everyone, today I'm going to explain the difference between traditional technologies and modern technologies. Let's start with the size and design. Old devices were big and bulky with parts both inside and outside the body. Modern devices are small, light, and more comfortable. They are easy to wear and not easily seen. Then let's go to signal processing. Traditional devices could only do basic sound conversion with limited features. Modern ones use advanced system with many channels, so the sound is clearer and more natural. Then the number of the channels. Old technology had only 1 to 4 channels, so the sound wasn't very clear. Now devices have 12 to 24 or more channels, giving us a more real detailed sound. Then sound quality. Traditional devices sounded robotic or flat, while modern ones give more clear, rich, and more natural sound, which helps people understand speech better. Surgical techniques. Before, surgery was more painful and took longer to heal. Today, surgeries are less painful and faster to recover from because of better tools and methods. Now let's go to battery life and power. Old devices used big batteries and didn't last long, while modern devices used rechargeable or wireless batteries that last longer and are easier to use. Then connectivity. For traditional devices, they couldn't connect to other gadgets, while modern devices now can connect with Bluetooth, smartphones, and even stream audios, making life easier. Customizability. Old systems had very limited settings, while modern ones let users adjust sounds in real time and personalize it for different places and needs. Compatibility. Before, devices were only used for hearing sound. Now they can connect to TVs, phones, and other systems, giving more ways to use them. And lastly, AI and machine learning. Old technologies didn't have any smart features, while modern devices use AI to filter noise and automatically change settings depending on the place, like reducing background noise in a busy area. And to wrap up, in short, modern technology is not just about better sound, it's also smarter, easier to use, and fits different people's needs better.
In the future, several improvements can make cochlear implant more effective and user-friendly. First, the use of artificial intelligence can help the device adjust sound automatically based on the environment, like reducing noise in busy areas without user input. Next, developing better biocompatibility materials can increase safety, reduce infection risk, and extend the implant's lifespan. We also suggest stronger connections to the auditory nerves, so users can hear speech more clearly and naturally. Wireless charging is another idea that offers convenience by removing the need to change batteries or plug-in wires, although safety studies are still ongoing. Finally, making implants more affordable and accessible, especially in low-income regions, is crucial to ensure more people benefit from this life-changing technology.